All right. Vincent, can you see the video?
Yeah, I can see him. Great.
All right. So let me play that video.
Course, and then get finished on a strong note because we're very lucky to have Vincent here with us. Vincent is an assistant professor at MIT, where he's been working on things related to scene representations, particularly neural scene representations, for problems in graphics, vision, robotics, etc. And we have spent a bit of time in this class talking about neural scene representations, and Vincent's work has really been at the forefront of a lot of these advances. For instance, one of the first works I remember reading, which optimized the instance-specific 3D representations, even before NeRF era, was something that Vincent was reading. That over the years, we've done a lot of moving work on improving neural architectures that are used for these representations, or coming up with new representations. And we've actually also covered several of the papers in the class, for instance, meta-SDF, type field networks, etc., etc. So yeah, at MIT, his groups have continued doing this along this excellent stream of work. And today, we are lucky that we have him here to tell us about the latest and greatest things, maybe with a bit of a focus on robotics. And yeah, with that, we let Vincent take over. Please, yeah, welcome him to the class.
All right. Great. Thank you, Shubham, for the introduction. But he won't be here to say that. But yeah. So let me stop sharing.
Yeah. So unfortunately, it says host disable participant screen share.
Oh, yeah. Let me just allow that. Yeah.
Yeah, now it works. Fantastic. Cool.
Yeah, perfect. All right.
Here. Yeah, thanks so much, Shubham, for the introduction. Shubham was actually apologizing that he couldn't make it in person, but honestly, I think the reason to get, one of the reasons to get a guest lecture, I'm more than happy to fill in for him also. And I'm glad actually that this gives him some flexibility to travel. This is always a little bit hard as a professor. So thanks for the introduction, Shubham. Yeah, so as I was asked, I'm going to talk about neural scene representations with a bit of a focus on vision and specifically robotics. And I'm actually talking about one paper that isn't actually even released yet. It's going to be released sometime this week. And it's very exciting to me, at least. I'm very excited about it, and really cool that I can be here. So some of you might already know the drill. I usually start my talks with a little interactive experiment, and I'm going to do this until this problem is solved. So I think I'm going to do this interactive experiment in variations for some time. So the little interactive experiment I'd like you to do is the following. I'd like you to, for a moment, just look around you. Some of you might be sitting in a lecture hall. Maybe you look at your backpack, or maybe at your laptop in front of you. Those at home can look at their desk and stuff. And I'd like you for a moment to close your eyes. And then I'd like you to reach for an object around you and pick it up. So for instance, this is my airport case. And then you can open your eyes, and that's it. I hope you succeeded. Most of you, I'm pretty sure, even though I can't see you, did succeed, I'm sure, at picking up a random object or maybe grasp the side of your table. And the reason why I do this little interactive experiment is because I want to make a point. As humans, we constantly interact with our 3D environment, and it comes very natural to us. We never think about it twice. But for a moment, just appreciate how incredibly impressive it is what you just did. So what you do here, right, is from just 2 videos, which are in your head, right, like your two cameras, you constantly reconstruct a 3D representation of the world around you. And that 3D representation doesn't only have the geometry and the appearance, which are maybe the obvious things, but it also has all of this information that allows you to interact with the scene, which is you knew upfront how heavy would the object be approximately, how hard would you have to grasp it, what is the affordance, like what grasp do you have to execute, in addition to the geometry and the appearance and all this stuff, right? Will it be cold to the touch, hot to the touch? All of these things you are inferring just from vision. Now you learn these, of course, using your other senses as well, but at test time, so to speak, your inference happens just from vision. It's extremely impressive. And at the end of the day, those are the kinds of systems that I want to build. I want to build systems that take images, take video as input, and they give you these 3D representations of the world that have all of that information that you need to be able to interact with the world. Now, the first question you might ask is like, how do we get the data for this, right? And it's worth noting that the data that you have as a human is basically interaction data, right? So you basically pop out of the womb, and then you bite stuff, you move your head around, you pick up stuff, you throw stuff. That's how you learn this model. And so that's what I also want to do. I want to build robots that learn these kinds of things self-supervised. And the thing that we're going to start with is just passive observations, but we're going to extend it to active observation as well. So first question, for what data? The data we are going to use for now is going to be egocentric video. So here's a data set called Epic Kitchens from Damen et al. This is a really cool data set you guys should check out. And this is just egocentric video, right? Now you can ask, what can you learn from egocentric video? You can learn a lot from egocentric video. Imagine the following objective. Imagine the objective is I give you frames of a video and I ask you what happens next. Give me a probability distribution over the next frames, or even just the next frame. And what can you learn in that way about the world? Well, any video you can think of to first order, you can break it down to 3 basic parts. One is the 3D geometry and appearance of the scene, right? Which is 3D geometry and appearance of the scene. The second is the camera motion, so the motion of the camera that is observing the scene. And then the final one is the 3D motion and deformation of the scene itself. So if you look at this unfortunate video on the left, right, you can imagine much of the variance in this video. In fact, the variance, every part of the scene that is static, is actually just explained by 3D and camera motion. And then there's a part that is related to the motion of the scene itself, which is the human in the scene and the objects that they're pushing around. Okay, good. So one area that we've made a lot of progress on in the past, I would say 50 years, since the 70s, since this problem started, is the problem of reconstructing static scenes that are mostly static. And static scenes are even easier because for static scenes, the variance of the video is like basically 99% explained by only the camera motion and the 3D appearance and geometry of the scene. So this video on the left, the only thing that isn't explained by 3D geometry and appearance plus camera motion is like lighting effects, like view-dependent effects, transparency, stuff like that. But as you can tell, like the variance of the video with respect to that is like actually not very high. So this is actually getting you pretty close. Let's for now assume that we know the camera motion. And I'm sure Shubham told you a lot about this already in this course. So of course, I assume by now all of you know about this all this differentiable rendering stuff, right? So if you assume that you know the motion of the camera and you know the poses of the cameras for the video, then what you can do is you can reconstruct the 3D scene via differentiable rendering, like neural radiance fields. Or Katerina, actually, I remember in my PhD, Katerina released some really cool papers concurrent with my deep voxels paper that Shubham pointed at. So this is like something that lots of people have worked on for a long time. But of course, it all kind of came to a head with NeRF in 2021. And this allowed you to do these like photorealistic 3D reconstruction, or almost photorealistic 3D reconstructions. So now the topic of this lecture is robotics. So I would ask, how can we use this stuff for robotics? So actually, you'll find lots of papers in the beginning. They used, these differentiable rendering techniques basically for 3D reconstruction. So it's basically like just a way of getting at good 3D geometry, and that's fair enough. However, it's kind of not exactly what we wanted, right? If you think our motivation is you want to have these rich 3D representations that encode all of these properties that we're interested in. So one important property is semantics. So one important property is for the 3D scene, we don't only want to know the geometry and the appearance, we want to understand semantically, like what is a bottle, what is a key, what is like an airport case, and so on and so forth. And if you think about these NeRFs, like the one on the left here, this is not what these models give you. These models are kind of like images with an extra dimension. And just in the same way as when you take a picture of a scene, the JPEG doesn't encode, like it doesn't have any explicit information about the semantic part of the scene. The NeRF also doesn't know anything about the semantic properties of the scene, right? This NeRF on the right doesn't have any tractable way of creating it for telling you that it's a playground. So that's a problem. And the reason for this is that, of course, this is kind of just a 3D data structure that we like use for 3D reconstruction. But and we fit it to images in that way. But I'm sure you are probably aware of these like kind of 2D, what we call sometimes foundation models. It's kind of a silly name, but here you can see this model called Dino V2 from Meta, which is really cool. And there's this cute dog that's running around. And on the bottom right, you can see a PCA of the features that this model gives you. So for every pixel, it gives you a feature descriptor. And that feature descriptor is highly correlated with what you would call like the semantic class of these scenes. And the important thing is this is fully self-supervised, so there's no labels necessary at any point in time. So we had an idea some time ago where we said, okay, NeRF allows us for every point to reconstruct a density and a color, but we want to understand the scene as well. We want to have these semantic features in the scene. What if we extend the 3D representation not to just give us density and color, but also such a semantic feature vector? And then what we can do is we can just make it so. And then for every image in our training set for a given scene, we just also reconstruct these per pixel semantic features. And now we will basically not only fit our NeRF, our 3D scene representation to the images, but in parallel, we'll also say that the rendered features have to match the features extracted from the images. And in that way, we can basically distill the features from the 2D images into the 3D scene representation. And so we called it distilled feature field. And we use this for like the key application that we pitched was for 3D editing. So here's a scene where we have NeRF, and these are the features that you extract. And you can see that these features are very semantically correlated with the class of the different parts. So you can see the ground, you can see the flower, you can see the leaves and stuff. And now because these are correlated with semantic classes, for instance, if you use features that are like language aligned, you can query it with a language word, with like a word. So for instance, you can say flower, and that just by like basically similarity, you can segment the scene into all the parts that are highly correlated with this query, which is the flower, or you can, and then you can edit it. You can like change the color and so on. Friends at MIT, Philip Isola's group, has recently shown that this is extremely useful for robotics. And I think it's not hard to understand why that would be the case. Imagine you have a scene, you reconstruct it, you get this feature field from it, right? Now you have given your robot a superpower. What is the superpower? You can now query any object. You can say, pick up the Baymax, right? Which is like this, I didn't know what that was. It's a plush toy from some Pixar movie, I think. And then the robot can immediately query the 3D scene representation and get the 3D geometry of only that object. And it will know where the object is, and it will know what the geometry of that object is. And then you can basically, everything else is hard-coded. You can basically hard-code algorithms for pick and place that then basically go and are able to manipulate this object. But really what this allows you to do is zero-shot manipulation of many, many objects that are just floating around on the internet. So you've given your robot a superpower, which is zero-shot manipulation of many objects. So this is really exciting. Philip and I are now collaborating on follow-up work to this, but basically distilled feature fields, like this idea of like distilling 2D foundation model features into 3D is a very powerful and very practical idea for robotics. So it's like very useful. I'll also point out that Katerina has done awesome work here. So I don't know if Katerina is in the audience, but I hope so. If so, hi. Here's a paper from Katerina called Act 3D, where they also use this 3D idea, this idea of distilling 2D foundation model features into 3D. In this case, they're using a point cloud, but I think Katerina also has some work on doing it with pixel NeRFs, so it's very exciting. So what's wrong with this? So first, these models are like the ones that are overfit to a single scene. They're not really scalable. So they need to reconstruct the scene from many images. Katerina's work and other folks at UCSD have made some progress on that. So like now we can kind of do it from fewer views. But the big thing that really irks me is that all of this understanding, quote unquote, really comes from the 2D model. Like basically, if you think about it, like all of the semantic heavy lifting actually comes from the 2D model giving you these features. And then we're just kind of making it multi-view consistent to get a 3D scene. So this is kind of not very satisfying to me, where my goal is, the goal should be in my eyes to like take video and from video self-supervised learn models that give you these 3D representations with all of these features you care about. So how could we think about doing that? So the first thing that I want to talk about is the idea of dealing with uncertainty. So what is going to be the objective? We're going to now switch gears a little bit. Instead of fitting a 3D scene from lots of observations of that 3D scene, like 100 images of a tabletop or something like that, we're now going to train neural networks like as follows. Going to take an image of a scene, like a single image or 2 images or something, give them to a neural network. The neural network is going to output some 3D representation of the scene, like a NeRF. And now the trick is that we can render that 3D representation with the differentiable renderer, and then we can supervise it just in image space with like a re-rendering loss. So now what we have done, instead of fitting a single scene, we can now go and train a neural network to reconstruct 3D scenes for us in a single forward pass, just by having a data set of lots of scenes with lots of observations for each scene, if that makes sense. There is an interesting problem if you do that, though, that is very relevant to robotics. And the problem is that of uncertainty. Let me visualize this for you. Here on the left, you can see like an image, right? It's an image of a fire hydrant. And now I could ask you, tell me what this fire hydrant looks like from the back. Imagine you take the camera and you move it to the back of the fire hydrant. You might tell me maybe it looks like this, or maybe it looks like this, or like this. And you can see all of these images are kind of similar in the sense that they are similar up to the kind of up to the things that you can glean from the input image. But the texture, for instance, is different. And if you looked closely, you could see that even the geometry is different from them. In fact, all of these are outputs from a 3D generative model that we trained. And what that model allows you to do is it allows you to go from a single image to a distribution over 3D scenes that is consistent with that image. Okay, so why is that important, right? So if you try to train the kind of model that I talked to just about before, where you train a neural network and it just gives you one reconstruction of the 3D scene, and you train that on lots of scenes, it always has this problem of basically bad reconstructions. So for instance, in this example, this model deterministically takes this input image on the left and it gives you this 3D reconstruction on the right. You can tell that this 3D reconstruction is really poor. It looks fine from the angle from the front, but if you look at the rest of the scene, the moment you turn the camera around, it becomes a blurry mess. And why is that? It's because these deterministic models, they have to average over all possible 3D reconstructions of the scene. So this model basically conditioned on the training set says, give me the image, I will give you kind of the mean, if you wish, of all of the plausible 3D scenes that are consistent with this image. And that is just very blurry and noisy. And for these fire hydrants, it's fine. But if you now go to like rooms or like environments that are more complex, and I ask you what is behind this door, and you open the door and you try to generate that part of the scene, it's going to be garbage. It's going to be a complete mess because you know the uncertainty is so high that this deterministic approach won't give you anything. How can we fix it? Well, I'm going to talk about a model that will allow you to instead sample from this uncertainty. So it will allow you to sample from the distribution of 3D scenes consistent with this image. And on the right, this is the output of our model. And here's the depth that we reconstruct. Okay, I'm going to give you the high-level idea because we also want to move on to some more robotics, to some more robotic stuff. So it's okay if you don't maybe understand all the details, but I do want you to understand the high-level idea. If there's questions, please feel free to just interrupt me. It's really quite cool. It's worth understanding. Okay, so all of you are probably familiar with generative models of images. So here's these outputs from like Stable Diffusion or something. Really cool. So we need to do something similar. We need to train a generative model because it's going to, it's going to generate 3D scenes. The big problem, of course, is we don't actually have a big data set of 3D scenes. So for images, it's easy, right? Diffusion models, the way it works is you take images, you add noise to them, and then you train a neural network to denoise that image, like 2-second version, right? For 3D scenes, please point me towards the data set of like 10 million 3D scenes that are reconstructed at high precision. And even if you had that, actually, it would be problematic. But you just don't have that. It's just difficult. The only data that we have actually at scale are videos of 3D scenes. But how can we train a generative model of 3D scenes if all we have is images of the 3D scenes? And differentiable rendering here is really the key. So the key idea that what we're gonna do now is we are also going to build a denoiser, but this denoiser is going to take a noisy image, and the way it's going to denoise it is by actually reconstructing the 3D scene and then rendering it again. So specifically, let me show you this figure here. I wish I was in person, then I could like spatially explain it to you. Unfortunately, over Zoom, it's a little harder. But the way it works is, imagine you have an input view. Like actually, let me give you this example. You have this boring object. Let me find a more interesting object. Here, here's my lunch, which I didn't eat. So here's an input view of this power bar, right? Now imagine what you're going to do is you want to render this view of this 3D scene, or you want to sample from the distribution of 3D scenes that are consistent with this image. What we're going to do now is we're going to basically pick a view of this object, like this one here, like a side view. And what we're going to train our neural network to do is basically say we want to denoise that view. So at training time, we assume we have this view in the training set. We're going to add noise to it, and now we're going to denoise it. But the way we're going to denoise it actually is we're going to take the input view and we're going to take that noisy view, and then we are using both to reconstruct the 3D scene in a single forward pass. And this is done via, there's lots of methods for it, but one good one is PixelNeRF from you et al. In 2021. So now you have reconstructed the 3D scene conditioned on the noisy image and the input image. And then you're going to render out both of them again. And you're going to call the rendering of this new view, that's your denoised image. So you're going to denoise the image by reconstructing the 3D scene and rendering it again. And that's the way how you can basically make the denoiser a part of the diffusion model. So there is some details I'm going to skip. Specifically, actually, what you need to do, it can't just be a noisy view. There's like some way in which you have to relate it to the input view, but on a high level, this is kind of what it is. Well, actually, let me just briefly walk through it. The way you kind of do it, there's many ways of doing it. This is how we did it. You first render out this deterministic estimate of this image. Like you basically input image, just render out the deterministic estimate, like this blurry image that we discussed before. And now what you do is you add noise, like you concatenate that with noise. And now you go through a second round of this denoiser that we just discussed. You use that to then denoise this image. And what that does, this conditioning input, this blurry estimate, what it basically tells the model is it tells it what parts of the scene are uncertain and what parts of the scene are not uncertain, and what is the scene generally like. And so it could be, for instance, that if you picked a view that has very little uncertainty, this estimate might already be pretty sharp. So then the diffusion model doesn't have to do much. But for instance, imagine you pick a view that is entirely uncertain. In that case, the diffusion model can take the hint and basically hallucinate everything. And there's some more details to this, but I'm going to skip them. So here's what this looks like. Here's the input. Here's the deterministic baseline. It's called PixelNeRF. And as we discussed before, it's rather blurry and kind of uncertain. Here's a model from actually Shubham's group. It's called sparse fusion. This is a very good paper, and I'm going to tell you about it in a moment a little bit more, although I assume Shubham already told you much about it. But for a variety of reasons, on this example, it doesn't work very well. But here's here's our reconstruction, and our reconstruction really gets you like these sharp samples with like uncertainty over the 3D scene. So let me talk a little bit more about sparse fusion, actually. Sparse fusion is really cool. And I like to put it into the same framework that we just discussed, because I think it will illuminate what the difference is and like what the benefits and disadvantages are of either method. So sparse fusion kind of works like this. You take the input image, your single input image, and then you render out this deterministic estimate, this blurry estimate that we just discussed before. But now what you do is you also stick that into a diffusion model, but this diffusion model is now just basically trained to make that image nice. So basically, instead of trying to going through a second pass of differentiable rendering, instead what you do is you take that image and you basically ask the diffusion model, what is a plausible sharp image conditioned on this blurry image? And if you look at the single images, it actually looks really good. And in fact, there's follow-up work to sparse fusion, which is called reconfusion, which is from folks at Google. But honestly, it's like very similar to the sparse fusion paper. So like, I think the groundwork for this was really laid by Shubham here. What you can see exactly is at the bottom, you see this like, you see the per frame estimates, and you notice how the per frame estimates are like very noisy. Like they flip from again and again. That's because you're running the diffusion model on every frame separately. But then you can do some post-processing, which is called score distillation, which basically seeks the mode of all of these images, and then that will give you a multi-view consistent 3D representation. And so this is also very useful, especially in computer graphics. The key difference here is that this doesn't actually give you a distribution over 3D scenes. It gives you a distribution over images of 3D scenes, and then you have to do a post-processing step to find one 3D scene. Versus the method we just discussed, it is a way of directly sampling from the distribution of 3D scenes. But both are useful and interesting. So here's some results of our scene trained on these room scale scenes. So given a single input image, you can basically pick another view and hallucinate the 3D scene. And what you can see here is, for instance, here the model allows you to move outside the room. So it basically generates like the door. Or here it generates the part of the scene that wasn't observed. So it hallucinates the trees and stuff. And let's zoom in on this kitchen scene here. So from a single input image, you can generate this 3D scene here. So note, this is not images. This is actually a 3D scene. This is a NeRF. You can render it from arbitrary views. And what you see here are samples. Each of these samples is one full 3D scene. So each of these is multi-view consistent and can be rendered in a multi-view consistent way. And what you see here on the right is the variance map. So for every pixel, we are plotting how much that pixel changes every time you sample. And exactly what you expect happens is that all the parts of the scene that were observed in the input view have very little uncertainty. All the parts of the scene that weren't observed in the input view are very uncertain. Cool. So like, I'm going to skip over the other examples. This paper was called Diffusion with forward models. The reason why it's not called 3D diffusion or something is because this is actually a method for training generative models for any latent space that you're observing through some differentiable forward model. So like the differentiable forward model here was differentiable rendering. But if you have like cryo-electron microscopy or something like that, you can still use the same framework to get a distribution over the latent scenes that you observe through that forward model. And it was led by Ayush and by Tianwei. So this is cool. Now, how does this relate to robotics? The key application that is actually kind of important to understand is that in robotics, oftentimes you have the case, just like you, in fact, that you have some incomplete observation of a scene that you want to interact with. And what you're doing isn't exactly keeping, you are exactly aware of the uncertainty. So for instance, for this cup, even though you can't see the backside, if I asked you to execute the graph virtually, you could totally do that because you know that the cup is round, right? But you would also maybe not be so surprised if you noticed that there was like a handle on the other side. And you can sample from the distribution of plausible 3D reconstructions. And that's actually something that's very important for robotics as well. Although we didn't explore robotics application in this paper. Cool. So here's a dirty little secret that we have so far not talked about. So all of the models that we just discussed, they require you to have access to the camera poses of lots of images. So for instance, the model like NeRF, for NeRF, you might know this, right? It requires you to have lots of observations plus the camera poses to fit the scene. But the other model that I just showed you, you might ask, why is it all indoor rooms and why is it like fire hydrants? And the reason is that those are the only two data sets back then that actually had camera poses at scale, where someone went through the extreme cost and the extreme pain to take all these videos and then run CallMap on them, which is like a bundle adjustment algorithm. It's extremely expensive, and still the camera poses are really bad. Like the Code3D data set, which I'm very grateful for, from folks at Meta, half of the camera poses are literally useless. It's kind of wild. Okay, so this is kind of a problem. We are relying on camera poses in all of these differentiable rendering algorithms. And now I'm going to talk about something really cool. I haven't talked about this before in public, so it's cool. It's the first time I'm talking about it. How could we get rid of this constraint of camera poses? So let me first go through two conventional approaches. One conventional approach is exactly the structure for motion or SLAM approach, like CallMap or DroidSLAM or OrbSLAM, which kind of work, but often they don't. And if they don't, you're kind of just screwed. And there's like lots of limitations that we don't like. Okay, and they're very expensive. The other one is like joint NeRF and pose optimization. So, but like really, you're also just optimizing the 3D scene jointly with the camera poses. And these are very inspirational. I'm very grateful for them, but they don't actually work. Like literally what I mean is if you take a video right now with your phone, you will not be able to reconstruct the camera poses and the geometry and the camera intrinsic parameters with these methods. There's other methods, which there's these self-supervised monocular depth estimation and pose estimation papers, which do work for self-driving. They only work for self-driving because the camera motion is really straightforward. It's basically just, it's literally straightforward. The camera is just moving into the scene and sometimes it's turning. But they don't work for like unconstrained video, like even of static scenes that you find on the internet. And then there's some really cool supervised learning work. Some of it from Shubham again, Cameras as Rays. Really cool paper, you should check it out. Or Duster, also really cool, that just came out. But it is worth noticing that all of these papers are supervised. So they require you to have a large data set of bundle adjusted 3D scenes. And I think that is a promising direction and practical. I think that just as envisioned before, in the long run, we have to bet on self-supervised methods. So I'm really interested in like, can we train a method that learns to reconstruct the poses and the camera parameters and the geometry of the scene just from video? No supervision, no annotation necessary, no pre-processing necessary, ideally. And I'm glad to, also something, this is wild, like just something to appreciate for a moment. Like, you know, structure for motion or SLAM is one of the oldest problems in computer science. It's like, it goes back to the 60s. Like literally before people could implement these things, people thought about how to do structure for motion SLAM. And it's kind of the only area of computer vision where the state-of-the-art method, which is CallMap, doesn't use any deep learning, no learned priors. It's all handcrafted optimization, and it's like very complicated. You can go and read the paper or the code. It's a mess. I mean, it's beautiful, and I'm grateful again for that it exists. But honestly, it's high time that we move past it. It has kind of constrained us. Okay, so we had this paper in NeRF last year. It's called FlowCam, and what we did here is we basically trained a model that was able to reconstruct these more complex trajectories where like a camera actually moves around something like outward in-facing scenes. Camera trajectories. And what the method does, it is in a feed-forward pass, it reconstructs the frame-to-frame camera poses, and it gives you a 3D reconstruction of the scene in the form of like a pixel NeRF. So that was really cool. It also really did work on lots of scenes, but it didn't work like that well. Like it actually outperformed like OrbSLAM on like some of these casually captured scenes, which was really cool. And I was really excited about it, but you know, it's not competitive with CallMap at this stage. Here was a scene that was maybe also really interesting. So it's a scene where the camera is moving around this outdoor object. On the bottom left, you can see one of these baselines. Barf it's called. Don't ask about the name, but it's a cool paper, but it really doesn't work. This model here was trained. This is feed-forward inference. So this is a model that feed-forward predicts the camera poses. And this is trained only on real estate 10K without camera poses. So really just training on videos. And we noticed back then that we can fine-tune this model, and then it gets like actually pretty good camera poses, like still not close to ComMap, but like pretty getting there. So we were intrigued. And we worked on this for the past year. And we got the following thing, which is called FlowMap, Differentiable Structure for Motion by Gradient Descent. And the name is exactly what it does. So the input-output behavior of FlowMap is that you assume you have a video, then you have optical flow for that video, which we compute off the shelf with like Raft or like some other optical flow algorithm. It doesn't need to be perfect. It's like fine if it's like not perfect. And in fact, Raft optical flow is often not perfect. And then we compute point tracks also with an off-the-shelf method. So point tracks and optical flow are both methods that are very, very surprisingly reliable on real-world scenes. Again, point tracks, I think Katerina has done some really cool work here. So go check that out. And here's what we can do with this. So from just, this is a video. So here's again the input, RGB video, optical flow, and point tracks. And here is our new structure for motion method that is only optimized via gradient descent. So here we're optimizing over the poses, the point cloud, and the camera intrinsic parameters just from gradient descent. Here's the point cloud that we get from that. And the point clouds and the camera poses are so good that we can actually use it as an initialization for Gaussian splatting. And these Gaussian splats are regularly on par or even outperform those Gaussian splats that you would get from ComMap. So these camera poses, so this method really actually works. So this is not something that kind of works. Like it works to the degree of you can take your iPhone out or your phone. You can take a little video of like some object. And like I would promise you that this method actually works on that video and you will get an actually good 3D reconstruction out of it. And the thing that is so exciting is that this method is a complete departure of these conventional structure for motion and SLAM methods, and it's fully self-supervised. So this is not using any camera annotations at all, no intrinsics, no poses at training time. And it works completely differently than ComMap. It is all via gradient descent, no second order solvers, nothing weird. And I'm going to explain to you now how it works. I'm going to actually start talking about the loss. So we are going to first set up the loss, and the loss itself tells you how can you get gradients for the poses, the intrinsics, and the depth. And then we'll go from there. So the loss, we call it a camera-induced flow loss. This is not our contribution. This is like well-known stuff. This is like well understood since the 60s. We're just going to give here a really good synthesis of this, or I hope a good synthesis of like what's going on. So the course, this loss is going to take as input our current estimate of the camera poses, that's P. It's going to take as input our current estimates of the intrinsics, that's K. And it's going to take as input the per frame depth, our current estimate of the per frame depth for every frame of the video. And it's going to assume that we have correspondences from optical flow and from point tracks. The point tracks are actually, either of them is like optional. You have to have one of them, both of them is better, but you only need one of them. Here's how the loss works. So let's assume we have a video. Now let's assume we look at 2 frames of this video, 2 consecutive frames, II and IJ. Now, consider that for one of them, for II, we have our current estimate of the depth map, right? This is our free variable. We are optimizing for this. So we have a per pixel depth. Now what we're going to do is we're going to unproject it using the current estimate of the intrinsics. So, and you can unproject the depth into a point cloud, correct? Like basically a pixel-aligned point cloud. Then we'll use our current estimate of the pose. And what that is going to do is it basically induces a flow, like a 3D motion vector on each of these points. Imagine it as such. Of course, you can keep the depth map fixed, and then you can move the camera. Or you can imagine equivalently, you keep the camera fixed, and you're moving the depth map by the pose, right? By the pose that you have. And what that does is it basically gives you for each point a little flow vector, like a 3D vector that tells you where it moves, from where it moves to where. And we call that scene flow. And the trick is now we can take that scene flow and we can project it onto the image plane using our intrinsics again. And that gives you optical flow. So optical flow is in fact exactly projected scene flow. So the optical flow that you observe in image space is exactly the projection of the 3D motion of each point. And this optical flow we can now compare to the optical flow that we independently computed using the video, right? So basically, this is a differentiable forward model. It's kind of like if you want a differentiable renderer for optical flow that explains optical flow in terms of 3D flow, right? And again, nothing fancy here. This is well understood for a long time. Good. Now let's do the obvious thing, right? We have a loss. It gives us an energy. We can minimize it. Amazing. So we're just going to take a video. We're going to initialize depth, poses, and intrinsics, and we're just going to go for it. We're going to minimize all of them via gradient descent. Unfortunately, that gives you complete garbage, right? So what you see here on the left, these are actually ablations, but basically we tried it out with like using the pose as a free variable, the depth as a free variable, the focal length as a free variable, and basically what you see on the right, imagine the squiggly lines is actually what you get if you try this. You've seen this before. This is basically what all of these like NeRF plus pose optimization methods would give you. So it just doesn't work. Why does it not work? The reason is because this problem is rife with local minima. In fact, you can imagine if you start with the wrong pose, it's really hard to change the pose of a camera. And note that the pose is independent from the depth. All of these are free variables. So there's like lots of solutions where it can make the optical flow look exactly right, but the geometry and the poses and the intrinsics are complete garbage. Womp womp. So this was a bummer. So how are we going to fix it? The way we fix it in FlowMap is we build differentiable feed-forward estimators for each of these variables. So instead of having per pixel depth for each of the frames, we're going to have a neural network basically that is going to predict the depth for each of the frames. Instead of having a pose estimate for each of the poses, we're going to, in fact, reparameterize the pose in terms of the depth that we predicted for each frame and the optical flow that we measured. And we're going to do the same for the intrinsics. So in fact, what we're going to do is we're going to build feed-forward estimators. Some of them are optimization-based. Some of them are neural network-based for each of these variables. And it turns out that what that does is it removes unnecessary degrees of freedom from this optimization problem, and it makes the optimization problem robust and tractable. I'm going to talk about two of these modules. The first one is going to, we already talked about the correspondence loss. That's the thing we just discussed, right? That's just the loss. It takes the pose, the intrinsics, and the depth as input, and it just gives you a loss. Now we're going to talk about the pose solver. So how can we solve for the pose? And so let's talk about the dumb way of doing this first. The obvious way is you're going to take like 2 RGB frames, you're going to concatenate them, you stick them into a neural network, and the neural network is going to predict the pose. That does not work very well. This is, it doesn't work, and there's lots of reasons for that, which we're not going to get into, but it doesn't work. So we have to be a little smarter. Here's what we're going to do. For 2 consecutive frames, I and j again, we take the depth maps, and now we're going to unproject the depth maps using our current estimate of the intrinsics, and that's going to give us 2 point clouds, right? For frame I and for frame j, it's going to give you point clouds. And the trick is that these point clouds are actually in correspondence because of the optical flow. The optical flow gives you pixel-to-pixel correspondence, but because these 2 point clouds are pixel-aligned, you now have 3D correspondence. And that essentially, again, gives you a 3D flow field. It tells you how one point moves from frame T, from frame I to frame j. And it turns out that this flow field, you can solve for the rigid body motion for the SC3 camera pose that best explains this flow field. And it's differentiable, it's feed-forward, it's not iterative. It's basically 1 SVD and like 4 matrix vector multiplications. And then you get the pose closed form. So the crazy thing about this is that this pose estimator doesn't have any free variables. This doesn't have any free variables. There's no neural network in here. It is all like, it's analytical. There's one little white lie here, but which is basically that you want to score the quality of the correspondences, but it's like not super important. And basically what this gives you is it gives you a differentiable estimator for the camera pose from frame to frame, where the only free variable is the depth. Like the only thing that you want to wiggle around is the depth. Everything else is known. So that's kind of wild. How do you get the depth? This one is straightforward. You're going to use a monocular depth predictor. But there is some subtlety here. So you're just going to use some network, pick your poison, and it's going to be some network that takes an image as input and gives you the depth. So now you might be compelled to say, well, this only works because you have a good monocular depth estimator that is pre-trained. But you're wrong. That's exactly not why it works. It works equally well if you randomly initialize this monocular depth estimator, or if you use a pre-trained one. The only thing that changes is how fast it converges. So if it's pre-trained and if you have a really good depth upfront, it's going to converge really fast to the correct depth and to the correct camera poses and intrinsics. But if it's not pre-trained, it still works. It just takes a little longer. So now you might be confused. At least we were confused about this. Because you might say like, okay, but if this thing isn't pre-trained, so if it doesn't use any priors, what is it doing? What could this convolutional neural network that is not pre-trained possibly be doing that helps us in solving this problem? And the answer is really cool. The answer is that all this convolutional neural network or any neural network can also be a VIT does is it says, for the same input patch, for the same RGB patch, I'm going to predict the same depth. It's kind of like a patch match regularizer. It's basically just saying if two image patches are similar, I want the depth to be similar. That's it. And in fact, this is a deeper insight about convolutional neural networks in general. Convolutional neural networks, no matter at which scale they're trained, they are all kernel machines, which means that what these models do is they take a patch in the input image, they compare it to all the patches that they have seen at training time, and then they will give you a linear interpolation of the labels of basically the center pixel, like the depth, for instance, of all the things that are seen at training time, and that's the prediction. It's kind of like a lookup in like a compressed hash map. There's no magic. Like MLPs have no magic. They're just kernel machines. So, deep learning is just kernel machines. Transformers are a little bit different, but whatever. So this is actually just enforcing a patch match regularizer. And so that's why it doesn't matter if it's pre-trained or not. It just means that if it's pre-trained, it has a faster convergence rate. But what this tells you is that this problem with this very mild regularizer is well conditioned. It works even if your depth initially is complete garbage, which is really important. But on the flip side, it also tells you if you have a perfect depth estimator, something really magical happens, which is if you have a perfect depth estimator and good correspondences, you will get perfect poses in a single feed-forward pass without any optimization. So you just take a video, you do a single feed-forward pass, and FlowMap will give you the correct poses and the correct depth maps for the, obviously the depth maps, but for the whole video. So in other words, like this reparametrization of the pose in terms of depth is really powerful because it gives you a feed-forward way of estimating poses only dependent on good depth. It's wild. Okay, the intrinsic solver works similar to this, but we're not going to talk about it because I want to talk about one more robotics paper. So if you put all of this together, FlowMap right now is a method that you can take any video and you can just fit like this like model to a video, and just by a gradient descent, it's like very straightforward. Like there's nothing weird in it. It's like the code is very compact, and kind of the only few variables of this optimization problem are the weights of the depth neural network, and there's these correspondence weights, which basically tell you how good correspondences are. But like we glanced over those. They are important, but like they're not very hard to understand. And it doesn't need to be pre-trained, but if it's pre-trained, it goes faster. It's kind of nice. So, and I earlier mentioned FlowMap really works. It really does work. So like here's a bunch of scenes. None of these are straightforward from a variety of data sets like Code3D, tanks and temples, LLFF, like lots of NeRF scenes. And at the top, you can see the depth maps that are reconstructed. Note that these are relatively low resolution for computational constraints. They can be higher resolution if you have more compute. But it doesn't matter in this case. The poses are at the bottom, and the poses are like really, really quite good. Here's more scenes. The playground scene from Tanks and Temples. There's the Triceratops scene. There's like the flower scene. I'm sure you've seen many of these. And importantly, you can run this also on casual captures like Code3D scenes. Here's the point clouds that you get. So this is by unprojecting the point clouds. This is what you get. And you can see that the poses and the point clouds are quite crisp, so it works. And now what you can do is you can take these point clouds and these camera poses, and you could use them as an initialization for Gaussian splatting. And the Gaussian splats that you get from that are regularly on par, or sometimes even better than those that you get from CallMap. They are still outperformed by CallMap plus multi-view stereo. And that is just the way it is right now. No one is actually using CallMap MVS because it takes like really long. Our method is a little bit slower than CallMap, but it's still much faster than CallMap multi-view stereo. But I think if I would have to make a bet, I wouldn't be surprised if in the near future we will also outperform CallMap multi-view stereo. And I'm really excited about this because this is the first time, to the best of my knowledge, that we have been able to build something that is actually competitive with CallMap, that doesn't work in the way that conventional SLAM works. And it is fully differentiable. So this is a differentiable method for structure from motion. Here's some of the Gaussian splats that you get from our method. And you can see that I mean, you can't see very much. They look very similar. That's because both of them are good. CallMap is on the right, FlowMap is on the left. Here's like the tabletop scene from one of the NeRF scenes. Here's a, oh, actually, I guess I don't know how good the videos are, because I guess I didn't tick the box for optimizing for video. I hope these videos are scrutable. They look really nice. Just imagine photorealistic novel views. And yeah, and some scenes like that are casual captures, like this one here, CallMap actually doesn't do very well at all. And here we actually outperform CallMap by a fair amount. And so this project was led by Cameron and David. Why am I excited about it? This is really a way of training, like, of any of the multi-view neural networks that you know. This is a way of training them self-supervised on videos. Instead of like bundle adjusting a bunch of scenes, which often breaks and stuff, here you have something that you can just train end to end. And to me, this is a major step towards like my goal, which is 3D understanding from any video. There's lots of cool directions doing this for dynamic scenes, for autonomous navigation, generalization. And the code is super clean because David is the case to be out soon. And it's gonna you can find it on my website. It's gonna be hopefully out like this week. Cool. The last little time that I have, I want to spend on one more robotics paper that I worked on. This is a little bit of an older paper, but I think there is a question that I want to raise here that I think is important to think about. Which is, there was lots of excitement for neural scene representations in robotics. And I mean, we did discuss some very cool applications, but I think it is worthwhile to ask yourself, what is it actually that, neural representations give us on top of just geometry and appearance? Right? Like if you use like differentiable rendering, cool, you get like a 3D scene out, 3D geometry. And that's cool, but like as we discussed initially, right, like what you have in your head is so much richer than just geometry and appearance. There is like priors you encode about objects and stuff like that, like uncertainty, all this kind of shenanigans. So this is an older paper. So this is like, this is just meant as a case study of like, here's one thing that actually neural networks can buy you that without neural networks, you might have a harder time of getting. This paper is called Neural Descriptor Fields. And the way this paper works, or like the problem that we're trying to solve in this paper is we want to have an object. We want to record a demonstration for manipulating that object, like this mug. Here's a pick and place task. And now what we want to do is we want to have very few demonstrations, like maybe 5 or 10. And from these 5 or 10 demonstrations, we want to be able to generalize to new mugs, to objects that we haven't seen before. Like for instance, here's a much taller mug, or here's a much smaller mug. And then we want to be able to have the robot copy these things. And we, in particular, want to generalize to poses that were never seen at training time. For instance, here's a mug on its side. This robot has never seen a mug on its side, but nevertheless, it can easily execute the pick and place task for this mug in this unseen pose. Okay, what's the magic here? So input, output, 5 to 10 demonstrations input, test cases are pick and place. So let's first talk about a very simple thing. It's always good to start simple. Imagine I show you a demonstration with an object, and now I ask you to execute the same task with the same object, but in a new pose. So like here, for instance, we are executing a grasp for this mug on the left, and now at test time, we have the same mug, it's just in a different pose. And assume you have perfectly observed this mug. You have observed the full 3D geometry of the mug. In this case, it's really easy. You can just inscribe a coordinate system. You can attach a coordinate system to the mug. And now all you have to solve is, and a coordinate system to the gripper. And now all you have to do is you have to basically register the point cloud of the mug that you saw at training time with the point cloud of the mug that you saw at test time. And once you do that, you can just like reproduce the same pose for the gripper, and then you're done. I mean, there's still lots of hard coding and boundary cases that you have to deal with to make sure that there's no collisions and motion planning and whatnot. But like, just think about the inference of the grasping pose for now, right? Okay, identical shape, straightforward. Now let's try to do the same for 2 different objects, but they are still kind of similar. They still have the same topology and the same object class, like semantically they're identical, but the shape is different. Now, if you try to do this and you try to like assign a coordinate frame to the mug on the left, and then you try to figure out what the coordinate frame is for the mug on the right, it will fail because registration fails. because you don't have correspondence between these different objects. So that sucks. What we want to do instead is we want to kind of find a local coordinate frame. You want to find a coordinate frame that says, I am grasping at the rim of this mug. And we attach this local coordinate frame, and then we want to basically ask what is the similar coordinate frame on the other mug. And then we can reproduce the grasp relative to that coordinate frame, and then it will be successful. Okay, so how does this relate to neural scene representations? You can kind of notice that everything is about correspondence. Takeo Kanada once said, what are the 3 most important vision problems? It's correspondence, correspondence, correspondence. I actually tend to agree. This is also, in fact, a correspondence problem. You can cast it as a correspondence problem. And what we're kind of going to do now is we're going to cast this as a correspondence problem, but kind of as a implicit correspondence problem. So instead of like explicitly matching correspondences between these 2 marks, what we're going to do instead is we're going to use a neural representation of these 2 marks to find these correspondences implicitly. Yeah, it's the same. Of course, you could do the same if you want to place the mug. You just need to pick a different coordinate frame, right? Like a placement is like you want to place the bottom of the mug on a table or something. Okay, so we want to correspond any local coordinate frame across instances of the same object class, and we want to use demonstrations to find out what these coordinate frames are and where they are relevant. That's what the neural descriptor fields do. The basic idea is as follows. You take an input point cloud of the object, you're going to encode it, and you're going to encode it into a neural like an implicit representation of that shape. In this case, we picked occupancy networks. So basically, we stick into a neural network. It gives us a function that maps a 3D coordinate to the occupancy, for instance, of that object, right? And now what we're going to do is we're going to view the, sorry, I actually got ahead of myself. For starters, actually, all we want is we want not a function that gives us the geometry. We want a function that matches every coordinate to a descriptor, to a local descriptor of that coordinate. So stick the point cloud into the encoder, get an implicit representation of the object out. Now, if we query that with the coordinate, we want a descriptor of that coordinate. And that descriptor should encode the semantic class, like the semantic description of this object. So up here, it should be rim, or like at here, it should be bottom, and so on. Okay, so it should vary between like semantic parts, and so on and so forth. And now what we want is we want that if we have 2 different instances, then picking the same point that is semantically at the same position, like for instance on the handle, should give us the same descriptor. Okay. Oh, okay. The problem, of course, is what happens if like the object is in a different pose. Like now, what happened is that the object is in a different pose. So like if we have an encoder that takes this point cloud as input, the encoder is not going to give us the same neural implicit representation of the object. So now this descriptor value that we previously got, it's going to change. Like when we rotate the point cloud at the input of the encoder, everything's going to go break. So what we did in this paper is we found a way of making this encoder SE3 equivalent, or rather we used a paper called Vector Neurons, and we built on top of that from Leo Gibas's group at Stanford. And that allowed us to make this encoder SE3 equivalent, which means that when we rotate the point cloud, the descriptor field rotates with it. So here's what that looks like. So we can basically take the object and we can rotate the object. And even though the object is rotating, these descriptors, they always stay constant. They rotate with it, right? It's exactly what you want. And now we had exactly this property that we wanted. I can give you 2 different, and I skipped over a bunch of stuff, but basically what we do is we pre-train our neural descriptor field on a bunch of objects. And the way we train it is actually just for reconstructing the shapes. And then by making it the descriptor field SE3 equivalent, we get this property that the neural network will give you the same output if you rotate the input point cloud and you rotate the query point accordingly. And then you can match these key points across instances and across poses. So on the top left, for instance, you saw we pick the mug, you pick a key point on the handle, and on the bottom, you see the point with the highest similarity is exactly rotating with the small mug, with the big mug, and it works. And this is then what allowed us to do exactly the tasks that we discussed earlier.
Here we show the robotic manipulation capabilities.
Give me a second. How do I disable the audio?
Here we show the robotic manipulation capabilities.
Okay, sorry for the audio.
In the real.
But basically, you can see here, this is now what it is exactly what enables us to like basically pick and place these novel objects. Okay. This was the last project I want to talk about. I'm going to teaser something else. we have like some really exciting paper forthcoming on another robotics project, which I had hoped was done by today, but it's not quite done yet. But it's going to be done soon. And this project is going to be about how can we control any robot just from vision. So I give you a camera, I point it at the robot. Can I learn to control that robot just from vision? The answer is yes. But I'm not going to tell you just yet how it works. But we'll release the paper soon, and I'm really excited about it. I hope I'll get the chance to talk about it again. But it's really quite cool. So this is going to be about like the reason why I'm bringing this up is because, again, it is worthwhile asking yourself from first principles, what is it actually that vision should do? How can vision help robotics? And if you think about yourself, one reason why you are so incredibly good at interacting with the world is because you can see your manipulator. We even have a word for it, it's hand-eye coordination. Hand-eye coordination is critical for you to effectively and efficiently interact with your world. And in robotics, the way you can kind of think about it is that for most robotics tasks, we kind of only rely on proprioception. We only rely on the sensors in the robot and on the measurements of the joint angles. We don't assume that we have like a closed loop controller that looks at the, like what you do. You do closed loop control of your manipulator with your environment. And that's something we're very excited about. So I would say, ask yourself, what can vision do for robotics? Like what actually from first principles is the role of vision in robotics? Okay, so what is my vision, or what am I excited about? We have made incredible progress for 3D reconstruction over the past few years. It's really wild. It's like the best time in computer vision ever, in my opinion. So really cool. We are almost at a point where we can really, for unconstrained video, unprocessed video, any video from the internet, dynamic, static, doesn't matter, we will be able to reconstruct it in 3D. It's going to be wild. This will unlock things that previously were impossible, in particular in robotics. Like you probably, some of you have a Roomba at home, your Roomba constantly eats your socks. That is so embarrassing. Like, it's so embarrassing that we can't build a Roomba that doesn't eat socks. I mean, has been some progress, but it still doesn't work. And they still suck. It's wild to me. Maybe the newest generation of Roombas is better, but like to me, it's always a little bit funny when people talk about the risk of like artificial general intelligence, and we don't even have a Roomba that cannot not eat a sock. I don't know. So I would promise, if I was in the room with you in 3 years from now, 2 years from now, I will be able to take up my phone, move it around, and I will be able to get a real-time dynamic 3D reconstruction of the scene, including parts of the scene that aren't observed. And I think this is going to be, for the first time, enabling us to train intuitive physics models. These are models that don't only reconstruct, but they also tell you, conditioned on the action you're going to take, or you can take, how is the 3D scene going to change? And this is like really important. We don't have that today. It's really like, it doesn't work. There's like, it's not that this idea hasn't been around. This idea has been around for a long time, but it doesn't actually work. Like, no model today exists that actually works like this. There's no model on the whole planet that I can take my phone, take a picture, and then actually, have a video of the scene, and then actually in real time predict what will happen next with any amount of like generality and plausibility. It doesn't work, but it will work soon. It's going to be really exciting. That's the end of my talk. All credit goes to my amazing students. If you meet them, all of us are going to be at CVPR more or less. Please meet us at CVPR. It's going to be super exciting. We also have, unfortunately, Cameron, who was a visiting researcher who led the FlowMap and FlowCam projects. He's leaving us for starting his PhD at USC. We are joined by Hyunwoo and by Eric, who are joining us at MIT, and it's going to be very exciting. So thanks for listening, and if we still have time for questions, I'm happy to take some.